Welcome to the deep dive.
Ever stop to really look at your reflection in a spoon?
Hey, yeah, it looks pretty weird sometimes.
Exactly. Today we're diving into why that is, exploring the fascinating world of spherical mirrors.
That's right. And we've got some great material here. Syllabus points, detailed explanations, everyday examples, all focused on these curved mirrors.
Okay, so let's nail down what we're talking about. Spherical mirrors. They're basically pieces cut from a hollow sphere, right?
Precisely. Imagine a shiny ball and you just slice off a section.
And whether it's concave or convex depends on which side reflects the light.
Yep. Concave is the inside curve, like the hollow of a bowl. Convex is the outer bulging side. You can sort of picture those diagrams we often see.
Gotcha. So our mission today is to figure out how these curves mess with light to make images and where we actually bump into them in real life.
Right. Because they're surprisingly common once you start looking.
So first things first, we probably need some key terms, to make sure we're all on the same page.
Good idea. Let's start with aperture. Aperture, that's like the usable area of the mirror, the part the light actually hits.
Exactly, the exposed surface that does the reflecting.
Okay. Then there's the pole, P.
That's just the geometric center of that reflecting surface, dead center.
Right. And center of curvature. That relates back to the original sphere it came from.
You got it. It's the center of that imaginary hollow ball, C.
So the radius of curvature, R, is just the distance from that center, C, to the mirror surface, the pole P.
Perfect. PC is the radius.
And there's a line connecting those 2 points, P and C.
Yes, that's the principal axis. Think of it as the main line, the axis running right through the middle of the mirror setup, PX in the diagrams.
Okay. Now, the focus, F, this seems important.
Oh, it's crucial. For a concave mirror, it's where parallel light rays all converge, like they all meet up at that one point after bouncing off.
They focus there. Makes sense.
And for a convex mirror, the parallel rays spread out after hitting it, but if you trace them backwards, they look like they came from a point behind the mirror. That's the focus for a convex mirror.
Ah, so it's a virtual focus in that case.
Exactly. The light doesn't actually go there. Now, the distance from the pole, P, to this focus, F, that's the focal length, little f.
Right. And there's a connection to the radius, isn't there?
There is, yeah. For mirrors that aren't too drastically curved ones with what we call small apertures, the focal length is simply half the radius of curvature. So FR divided by 2.
That's a handy shortcut.
Yeah.
F equals R over 2. Okay.
Very handy. Now, to really feel the difference between concave and convex.
The spoon. Right. Our sources mention using a polished spoon.
Yep. Look into the inside curve first, the concave side. Hold it close.
Okay, doing it now. Metaphorically, I see myself upright and bigger.
Right. Now, slowly move it away from you. What happens?
It flips. Now I'm upside down, inverted.
Exactly. Now, flip the spoon over. Look at the back, the convex side.
Okay, right side up. Erect, but smaller. And yeah, still smaller, even if I move it closer or further away.
See, that simple spoon shows the fundamental difference. Upright and magnified close up, then inverted for concave, versus always upright and smaller for convex.
That's actually a really great illustration. So how do we predict where these images form without a spoon?
That's where ray diagrams come in. They're like little maps for light rays.
Okay, what are the ground rules?
Rule 1. You need to trace at least 2 different rays starting from the same point on the object. Where those reflected rays or their extensions cross, that's where the image of that point forms.
Makes sense. 2 lines to find a point.
Rule 2. Obvious, maybe, but the object has to be on the reflecting side. No reflection from behind the mirror.
Hey, right. Don't put the object behind the shiny bit.
And rule 3, just for simplicity when drawing, we usually put the object standing straight up, perpendicular to the principal axis, with its base right on that axis.
Got it. But which rays do we actually draw? There must be billions bouncing off.
Well, thankfully there are a few convenient rays that follow predictable paths. We only need 2 of these.
Okay, lay them on me. What's the first convenient ray?
Okay, first one. A ray that travels from the object straight through the center of curvature, C, when it hits the mirror.
It hits head-on, perpendicular.
Exactly. So it just reflects straight back along the same line it came on, retraces its path.
Simple enough. Ray number 2.
A ray that starts parallel to the principal axis. When this hits a concave mirror, it reflects and passes right through the focus, F.
Through the focus. Okay. And for convex?
For a convex mirror, that same parallel ray reflects as if it came from the focus behind the mirror. It diverges, appearing to originate from F.
All right. Third ray.
It's basically the reverse of the second one. For a concave mirror, if a ray goes through the focus first and then hits the mirror,
It reflects parallel to the axis?
bingo. And for a convex mirror, if a ray is heading towards the focus behind the mirror, it reflects parallel to the axis.
Okay, so parallel becomes focus, focus becomes parallel. Got it. One more.
Last one. A ray that hits the mirror right at the pole, P.
Right in the center.
This one reflects symmetrically. The angle it comes in at relative to the principal axis is the exact same angle it bounces off at, like a snooker ball off a cushion, using the axis as the normal line, essentially.
Angle of incidence equals angle of reflection applied at the pole.
Cool. So armed with these rays, we could figure out the image for a concave mirror anywhere we put the object. Let's start really far away. Object at infinity.
Like a star. All the rays coming in are basically parallel, right?
Exactly. So they all hit the concave mirror and reflect.
Through the focus. F.
Right. So the image forms at S. It's real because the rays actually meet there. It's inverted upside down. And it's tiny, highly diminished, just a point.
Okay. Now bring the object closer, but still further out than C, beyond the center of curvature.
Okay, trace the rays. Say one parallel through F and one through C back on itself. They meet.
Somewhere between C and F?
Yep. The image is still real, still inverted, but now it's a bit bigger than a point, though still smaller than the object itself. Diminished.
Okay. Moving closer. What if the object is right at C?
If the object is at the center of curvature, the image forms right there at C, too. Still real, still inverted, but now it's exactly the same size as the object.
Whoa. Object at C, image at C, same size. Interesting symmetry.
Isn't it? No, closer still. Between C and F.
Okay, my ray diagram intuition says the image is forming further away now, beyond C.
Got it. It forms beyond C. It's still real, still inverted, but now it's magnified.
Yeah.
Bigger than the object.
Ah, so we crossed the same size point at C, and now it's getting bigger.
Precisely. Now for the really interesting spot between F and P. Object really close to the mirror.
Closer than the focus. Okay, if I trace a parallel ray, it goes through F. If I trace a ray towards the pole, it bounces off. These reflected rays are spreading out. They don't meet.
They don't meet in front of the mirror? No. But what if you trace them backwards, behind the mirror?
Ah, they look like they're coming from a point back there.
Exactly. That's a virtual image. It's not formed by actual crossing rays.
Yeah.
And look at its orientation.
It's upright.
Erect.
And it looks bigger. Enlarged.
Yes. Virtual, erect, and enlarged. This is the magic behind magnifying makeup or shaving mirrors.
Yeah.
You put your face close, inside the focal length.
That makes perfect sense now. Okay, one last place for concave. What if the object is exactly at the focus? F?
If the object is precisely at F, the rays that go through C reflect back, and the rays that hit the pole reflect. Actually, all reflected rays end up parallel to the principal axis.
So they never meet.
They never meet. Or you could say they meet at infinity. So the image is theoretically formed at infinity. It's real, inverted, and hugely magnified.
Wow. Okay, that's quite a range of possibilities for concave mirrors. What about convex? You said they were simpler.
Much simpler. With a convex mirror, it almost doesn't matter where you put the object. Well, the position matters for where the image is, but not its basic nature.
Meaning?
Meaning, for any object position in front of a convex mirror, the image is always virtual.
Always behind the mirror.
Always behind the mirror, yes. It's always erect, right side up, and it's always diminished, smaller than the object. Always, always, always.
No exceptions.
No exceptions. The image always forms between the pole P and the focus F, behind the mirror.
Huh. But does anything change as I move the object?
Yes.
Yeah.
As you bring the object closer to the convex mirror, the virtual image also moves closer to the mirror surface, and it gets slightly larger.
But it never gets as large as the object itself.
Never. Always smaller. This constant, upright, smaller image that covers a wide angle is key to its uses.
Which leads us nicely into applications. Where do we use these things? Let's start with concave.
Okay, concave mirrors. Their focusing ability is key. Think reflectors in torches.
Flashlights, yeah. And car headlights, searchlights.
Absolutely. You put the bulb near the focus, and the mirror gathers the light into a strong, parallel-ish beam.
What about solar cookers?
Same principle.
Yeah.
Big concave dish focuses sunlight onto one spot, gets it really hot, and huge telescopes use massive concave mirrors to gather faint starlight.
And we already mentioned shaving and makeup mirrors using that close-up magnification effect.
Right. Object between F and P gives that virtual, erect, magnified image. Dentists sometimes use small ones too, and ENT doctors might use a concave head mirror to focus light.
You also mentioned floodlights. That seems counterintuitive if they focus light.
Ah, but for a floodlight, you put the bulb between F and P. Remember what happens then? The rays diverge after reflection.
Oh, so instead of a focus beam, you get a wide spread of light. Clever.
Exactly. Now, convex mirrors, their big selling point.
That wide field of view, even though things look smaller.
Precisely. So, number one application.
Car wing mirrors, rear view mirrors. Objects in near are closer than they appear.
That's the one. Gives you a wide view of traffic behind you, always upright, even if distorted slightly in size. Also used in some streetlights as reflectors to spread light out.
And those big round mirrors you see tucked into corners and shops.
Vigilance mirrors, yeah, security mirrors. Same idea, wide-angle view to see large areas easily.
So useful in very different ways. Now, our sources also briefly touch on something called dispersion. Related to reflection, but different.
Yeah, it's more about what happens when light passes through something, like glass or water, rather than bouncing off. It's about the colors within white light.
Like a rainbow.
Exactly like a rainbow.
Yeah.
White light, like sunlight, is actually a mix of all the colors.
Yeah.
Red, orange, yellow, green, blue, indigo, violet. VIBGYOR.
And when that white light hits, say, a prism or a raindrop, the different colors get bent by slightly different amounts.
That's the key. They get split up, dispersed, forming that spectrum of color. The raindrop acts like a tiny prism.
And there's that cool demo mentioned, the colored disc.
Newton's disc, yeah. Paint a disc with the rainbow colors, spin it really fast.
And it looks white. Or grayish white, because the colors blend back together in our perception.
It shows that white light is indeed a combination of those colors. And the prism experiment itself clearly shows white light going in and the rainbow coming out. It's a beautiful phenomenon.
Definitely related to light, but distinct from mirror reflection. Okay, so let's try and wrap this up. What are the big takeaways from this deep dive on spherical mirrors?
Well, I think the main thing is how the shape of the curve dictates everything. Concave mirrors converge parallel light, can magnify things up close, and produce both real and virtual images depending on object distance.
While convex mirrors always diverge parallel light, always give you that wide angle, upright, smaller, virtual image.
And these different behaviors lead directly to their uses, focusing light for headlights and telescopes, magnifying for makeup mirrors, or providing wide views for safety mirrors.
It really is amazing how just curving a surface changes so much.
It makes you think, doesn't it, about how simple geometry can manipulate light in such powerful ways, and maybe consider other optical things you see daily.
Like light bending through a glass of water or reflections off windows. How do those work based on similar principles?
Exactly. The fundamentals we've talked about, reflection, how images form, they're just the start. There's a whole world of optics out there.
Well, this has certainly given us a solid look at spherical mirrors, a great foundation. Thanks for exploring this with us.